Good afternoon, students. Welcome to our physics class. That is ray optics. So this is MSET related, right? So whoever followed in the morning, that mostly discussed it formula wise. So if you are comfortable with that, we can directly solve the problems. A little bit. Meanwhile, I have added some topics and some formula related. Okay, right. See, the first one of the points to remember related to this plane mirrors concept. By keeping the incident ray fixed, right? The mirror is rotated by an angle theta about an axis in the plane of mirror. The reflected ray is rotated through an angle 2 theta. This point is to be remembered. What is that? Keeping the incident ray fixed. Observe the diagram. In the first diagram, the incident ray is incidenting exactly normal to the plane mirror. Okay, M dash is the mirror. The O is the center point. Then what we learned that when the incident ray is normal to that, then the reflected ray also along that normal line. So there is no angle of incidence or reflection. So now observe this diagram. Incident ray is as usual. Incident ray is along in this direction only. But now what we have done, this M dash just made an angle theta here. Okay, with the vertical, it's made a theta here. Observe this then. Now the reflected ray is reflecting with the normal by making some angle here, theta. See, this dotted line is normal now. You should know that normal is always perpendicular to the mirror, plane surface. So this is plane surface and this dotted line is normal. Then incident ray is fixed as usual and the reflected ray is like this. So with the help of the normal, incident ray is making theta and reflected ray is also making theta. So total angle is 2 theta between the incident ray and reflected. So what we have done here, just we made deflection of this mirror at an angle theta, then reflected ray is making angle 2 theta. Initially, there was no angle between incident ray and reflected ray. But the moment a mirror is deflected for a small angle theta, then angle of refraction will be doubled. That's what is the meaning. Okay. So on this regard, we do one problem. So here a beam of light from a source, L. Let us take light, L means light. So is incidented normally on a plane mirror, which is fixed at a certain distance x. Right now, yeah. So distance x from the source. Now the beam is reflected back as a spot on the scale placed just above the source L. We should picturize this. When the mirror is rotated through a small angle theta, then the spot of the light is found to move through a distance y on the scale. Then asking what is the angle deflected by. Okay, so there is a source L. It is the light is normal to the plane mirror, and another at another distance x, which is arranged at a distance x from the source, and the beam is coming back with a spot is incidented on the scale just above the source. Then when the mirror is rotated through a small angle, then what will be the, okay, so what will be, yeah, it's observed the spot is on the scale, then what will be the angle they're asking. Okay, right. So now we'll move on to the solution here. Yes, observe this. Observe the diagram first. Here is the mirror. Means initially it was like this. Initially it was like this. Then, so this is the length source L, which is at a distance x, is incidented on the mirror. Now the mirror is reflected with some angle, then the spot appeared at this point. At this point, then he said no, that above the L, above the source. So the spot is observed just above the source, that is at a distance y. Then is asking what is the theta here? What is the theta? And theoretically, that we understood just now that when initially the mirror was like this dotted line, like this, the light ray is incidenting normal to the dotted line and L to theta, this one, L to this part. Both are perpendicular normal. So there is no question of reflection. But now what we have done, the mirror is reflected with an angle theta. Then what we learned, then the angle between the reflected ray and the incident ray is 2 theta. So this is the information. Okay, so now look at this. When mirror is rotated by theta angle, reflected ray will be rotated by 2 theta angle. So for small angle theta, so 2 theta becomes tan 2 theta. So look at this, tan 2 theta here. So it's a very small angle, so it's a very small angle, so it will become 2 theta is equal to y by x. So tan theta. Okay, opposite side by adjacent. So y by x. So theta is equal to, so take out theta here. So theta is equal to y by 2x. So that's what is the option, y by 2x. D option is correct. So based on that small concept, what is that? Whenever the plane mirror is rotated certain angle theta, whatever angle, for example, 10 radians, 10 degrees if it is rotated, then the angle between the incident and reflected will be double, 20 degrees. If the angle is 45 degrees, then the angle of this one, deflection of the mirror, then the angle between the incident ray and reflected ray will be double, means 90 degrees. Okay, so that is only the logic. Now we'll see one more. Two plane mirrors are inclined. Cautiously, check it out. Two plane mirrors. Okay, two plane mirrors are there, inclined at an angle 70 degrees. Means both the mirrors are just arranged such that the angle between them is 70 degrees. Now a ray incident on one mirror at an angle theta. Okay, one of those two mirrors, a light ray is incidented on that with an angle theta. Then after reflection, falls on the other mirror, second mirror, and it is reflected from there, reflected from that second mirror, and is traveling parallel to the first mirror. Traveling parallel to the first mirror. Then what could be the angle of incidence is asking. So here is the diagram. Here is the diagram. This one and this one, both are mirrors. The angle between them is 70 degrees is given in the plot. Okay, 70 degrees is given. Now a light ray is incidented. A light ray is incidented with a certain angle to the normal. Remember, to the normal. This is the dotted line. Okay, so with the normal, it is making angle theta, and exactly the same angle. Okay, reflection also takes place. This is reflection. Okay, and incidented. Okay, from the mirror, from the first mirror, the light ray is reflected and incidented on the second mirror is given in the problem itself, and condition is given. From the second mirror, the reflected ray is exactly parallel to the first mirror. That hint is given. Okay, the reflected ray from the second mirror is parallel to the first mirror, right? And only thing is 70 is given, this 70. So once this ray is parallel to the first mirror, then second mirror, so with the second mirror, this reflected ray also makes 70 degrees. This is 70, then this is also 70. Okay, so if this is 70 and this will also be the 70, because this incident ray and reflected ray. Okay, 140 angle. So remaining is how much, right? So here theta angle that we don't know. Okay, theta, right? So theta plus 40. So if this is 70, this is 70. Okay, then this will be 40, right? So theta plus 40 is equal to 90 degrees. Theta plus 40 is equal to, look at this, theta plus 40 is equal to 90. These two are making 90. So from that you can calculate theta. So theta is equal to 90 minus 40, that is equal to 50, right? So with this, what you understood, that angle of incidence and angle of reflection lie on the same plane and equal angles. Right, here is one more concept. When the object is in the denser medium. See, in the morning we discussed what is denser medium and the rarer medium. So denser medium means in which the velocity is less, means very slow. Density is more, means particles will be more than velocity will be decreasing. See here, when the object is in the denser medium and the observer is in the rarer medium. Example is a coin. Okay, a coin dropped in the bucket of water, right? So water is a denser medium comparing with the air. Now we are observing from top. We are observing from top, that is from air medium, that is rarer medium. So then how this will appear? This is what, when object is in denser medium and observer is in rarer medium, then what is the case here? Apparent depth. Apparent depth. Actually, original depth will be there, but due to the change in medium, what happens? We cannot see the object with the same depth. We cannot see the same object with the same depth because refraction takes place. Means the angle of vision will be different. So apparent depth. So definitely that coin appears that it is just embossed. Means just it's moving up. Appears originally the depth of the bucket will be something. original value. But apparent depth, because due to the change in medium, what happened? Apparent depth is different. That is definitely less than the original. So why it is happening? Because why it is happening? Because it is a change in medium, that is change in refractive index. Change in refractive index. Yes. So change in refractive index, that is refractive index of the what's a denser medium to the rarer medium, means with respect to the rarer medium, is equal to real depth by apparent depth. Original depth will be something, and the apparent depth will be something, means what we originally something and what we can able to see is something. So that ratio gives what? Refractive index of the particular medium with respect to the rarer. So here is the related problem. A bubble in the glass slab. Glass slab means a glass material with a certain thickness. Okay, a bubble in the glass slab, that is whose refractive index of that is given, mu is equal to 1.5. Mu is what? Refractive index. Actually, refractive index of air is 1. Okay, so that is the least value, and definitely all the media are more dense than air, so the value will be definitely more than 1 for the remaining materials. So here glass slab value is given 1.5. When viewed from one side, a bubble is struck in the glass slab. While viewing from one side, it appears at 5 centimeters. It appears at 5 centimeters and 2 centimeters from other side. Okay, because why it is happening? Because due to the change in medium. And then the thickness of the slab is okay. So what information is given? Just two sides dimensions are given and the refractive index of this material is given, right? So options are given like this, and the total apparent depth, okay, how much it will be? Y is equal to y1 plus y2 is equal to 5 plus 2 is equal to 7. So appears length, all these are what? Centimeters. Appearing lengths. From one side you are getting 5 centimeters, but from the other side you are getting means distances. Okay, and from the other side 2 centimeters. So the net will be what? 5 plus 2, that is 7 centimeters. And if x is the real depth, that we don't know original depth. If x is the real depth, that is equal to thickness of this slab. That is equal to thickness of the slab. Then yeah, then so mu, we have a formula. Mu is equal to real depth by apparent depth. Real depth by apparent depth. So one side we got 7 centimeters, and the other side we need to calculate x value, and mu value already given in the problem 1.5. I hope you understood that mu is equal to real depth by apparent depth. Here is given apparent depth from one side is 5, other side is 2. Then we calculated the net, that is what? 7 centimeters. And the refractive index of that glass plate is given mu, and real depth we need to calculate that. This is the formula, x by y is equal to 1.5, right? So or x is equal to mu y, and mu value is given 1.5, and net apparent depth value is given 7. So this is what 10.5 centimeters is the original depth, that is real depth. And is related to the total internal reflection or critical angle related, right? So here a ray of light traveling in transparent medium. A ray of light traveling in transparent medium. We identify each and every word is given in this. A ray of light traveling in transparent medium of refractive index mu. So transparent medium refractive index is mu. Falls on the surface separating the medium. Falls on the surface separating the medium from air at an angle of incidence of 45 degrees. Right. So the ray is initially traveling in transparent medium whose refractive index is mu, falls on the interface of two media, that is this transparent medium and air medium at an angle of incidence 45 degrees. Okay, so the ray is incidented on the interface of this transparent medium and air medium at an angle 40 degrees. Now, for which of the following value of mu the ray can undergo total internal reflection? So he's asking what will be the mu value such that when the light ray is incidented at 45 degrees, it should come back with the same light ray. It should come back into the same medium. So what would be the refractive index of this medium he's asking? And we know the formula. Critical angle is asking what? Total internal reflection. In condition, we should know that what is the condition for total internal reflection? The angle of incidence should be greater than critical angle. Greater than critical angle. Then only the light ray reflects. So for total internal reflection, sin I is greater than sin C. Means sine of angle of incidence is greater than sine of angle of critical angle. Yes or no? When the light ray is greater than this angle of incidence, which is critical angle, then where I is the angle of incidence and C is the critical angle, then we know the formula sin C is equal to 1 by mu. Okay, sin C is equal to 1 by mu. It's from the Snell's law. Sin C is equal to 1 by mu, and sin C, that what we wrote here, sin C is what? Sin I. Sin C is nothing but what? Critical angle at which the angle of incidence such that the angle of incidence is critical angle, so that what happens? The angle of refraction becomes 90 degrees. So sin C is equal to 1 by mu, therefore sin C is nothing but incident angle is greater than 1 by mu. Yes or no? Greater than 1. Or just you can write this, mu is greater than 1 by sin. Just you're rearranging this. Now, but what is the problem? In the problem, what information is given? Angle of incidence is 45 degrees. The problem is given angle of incidence is equal to 45 degrees. So here sin 45 will be substituted. So mu is greater than 1 by sin 45. Yes or no? So mu is greater than, okay, root 2. So here mu should be greater than root 2, then total internal reflection takes place. And the root 2 value is 1.4. Yeah. What is the option C? 1.414. Yeah, the answer is near to the B. Okay. Right. So this is the procedure. Okay. Right. And this is related to what? Critical angle and total angle. Right. And we'll see the next problem here. The speed of the light in medium. The speed of the light in medium. The speed of the light in medium m1 and m2 are, right? The speeds are given. There are two media, m1 and m2. In one medium, it is moving with this much, 1.5 into 10 power. Who is moving? Light. Okay. In 10 power 8 meters per second and 2.5 into 10 power 8 meters per second respectively. But originally, what is that? 3 into 10 power. Okay. Is half. Okay. Right. So A ray of light enters from medium 1 to medium 2. Medium 1 to medium 2. So 1.5, it is 2. So this is a rarer medium, this is denser medium. Right, at an incident angle I. So from one medium to another medium, the light ray is incidented at an angle I. If the ray suffers total internal reflection, okay, then what is the value of I? So he's asking angle of incidence. So what could be the angle of incidence such that total internal reflection takes place? Total internal reflection means, what is the condition? The angle of incidence should be more than critical angle. So that we need to calculate what is the I value. Okay, so these are the options. We'll come back to this one. So here is the solution. Refractive index of medium 1. Refractive index of medium 1. Already in the morning, we discussed what is refractive index definition. Okay, so refractive index definition, mu is equal to velocity of light in air to the velocity of light in medium. So in medium 1, the value is given 1.5 into 10 power 8, and velocity of light in space, air, is fixed. Then we are getting 2. Okay, 3 by 1.5 is 2. So what is this? Refractive index of medium 1. Why it is required? Because critical angle relation we have, sin C is equal to mu 2 by mu 1. In the morning we discussed sin C with respect to mu, with respect to velocity, with respect to density we discussed. Right, so the refractive index of first medium we got 2 here. And if you see the refractive index of the second medium, the same procedure, and we are getting C by V2. So 3 by 2.0, 3 by 2, it's a 3 by 2 you are getting, right? Now the total internal reflection, yes, don't forget this relation, that sin I is greater than sin C. Sin I is greater than sin C. Right, so where I is the angle of incidence and C is the critical angle, and we know the relation sin C is equal to mu 2 by mu 1. So we have the two values, 2 and 3 by 2. So sin C is what? Critical angle. So that angle of incidence should be greater than, yes, should be greater than. Yes, sin C is equal to mu 2 by mu 1. Sin C is equal to mu 2 by mu 1. But we don't want sin C. We need just greater than that, because condition is what? Total internal reflection. So sin I is greater than C means what? Mu 2 by mu 1. Okay. So sin I is greater than or equal to, okay, mu 2 by mu 1. So here mu 2 value is how much? 3 by 2 and by 2, and it will be 3 by 4. So sine inverse of this is asking I. So take out I, then sine inverse of how much it is? 3 by 4. Okay. So the option is 3 by 4. Yeah. So C option is correct. That is equal to or greater than sine inverse. Okay, greater than sine inverse. That is important. This is important. Because it's asking total internal reflection, then angle of incidence should be greater than 50. Now we see the next problem. Very cautious. A small coin, it's a depth related one. A small coin is resting on the bottom of the beaker filled with certain liquid. Imagine a ray of light from the coin, travels up to the surface of the liquid and moves along its surface. How fast is the light traveling in the liquid? See what is asking. Velocity of light is asking. See, options are in terms of meter per second, so it's a velocity, right? A small coin is there. See, observe in the compare with the previous diagram, that coin example problem we discussed. That was what we observe from the rarer medium to the denser medium. But now the whole story, the thing is happening inside the denser medium, some liquid. It's no way concerned to the air here. But observe this, the coin is here. From the coin, whatever the light is there, which is coming from the coin, right? The moment it is reached to the surface, sorry, interface. Surface is nothing but what? Interface of two media. Surface is nothing but interface of two media, that is water or liquid and air. So there it is not refracting. Instead of refracting, it is refracted through interface. Through interface. Instead of entering into the other medium, it is traveling through the interface. So dimensions are given like this. The depth of this beaker is given 4 centimeters, and shift means from original to the this point. Okay, so 3 centimeters. So this information is given. So I'm repeating here, a small coin is resting on the bottom of the beaker filled with the liquid, and a ray of light from the coin travels up to the surface of the liquid and moves along its surface. Then how fast is the light traveling in the liquid is asking, right? See what information is given. Yeah, just like that here. Now from the figure, sin C is equal to, we don't know any dimensions over here, even we don't know any angle over here. Only thing is, only one information we understood is, when the light ray is incidented at the interface, it is neither reflecting into the same medium nor entering into the other medium. It is moving along the interface. Means what is this angle of incidence? This is critical angle. So sin C is equal to sin from, this is the triangle here. This is the triangle. So yeah, what you observe. So 3 by we can calculate this hypotenuse. Okay, opposite adjacent, and this is hypotenuse. Sin C is equal to opposite side by hypotenuse. So that's what is under root 4 square plus 3 square. How much it is? 16 plus 9, 25. So under root 25 is 5. Right. So what you have observed here. So this side is 5 here. So this is the dimension we are getting. Now where C is the critical angle, and also we know the sin C is equal to 1 by mu. Okay, 1 by mu. So relation that we know. Right, sin C is equal to 1 by mu. That is, since 1 by mu of what is that? Is given liquid and air. Liquid and air means mu of liquid with respect to air. So sin C is equal to, okay, so 1 by mu, right? Now also, what is that? Mu of air with respect to, so mu of liquid with respect to air. That's what is the formula. Velocity of light in air to the velocity of light in liquid. That gives the refractive index. That gives the refractive index. That is C by V. So sin C is equal to, yeah, here mu is equal to C by V, but sin C is what? 1 by mu. So sin C is equal to 1 by mu 1. So sin C is equal to V by C. Sin C is equal to V by C. So that is equal to V value we need to calculate, and C is the velocity of light is fixed. That is 3 into 10 power 8 meters, right? And Yeah, sine C is equal to V by 3 into 10 power 8. And take out V, and sine C value here we got 3 by 5. So therefore V is equal to this much into 3 by 5, and how much are you getting? 1.8 into 10 power 8 meters per second. That is 1.8 into 10 power 8 meters per second. 1.8 into 10 power 8 meters per second. That the D option is correct. So this is the way to get the velocity. Only thing is you should be very up to date with all the formulae. Okay, so all the relations you should be keep in mind. Right, we'll move to the next problem now. Yes, for the given incident, ray is shown in the figure, right? Incident ray is there, okay, which is incidenting on the interface with an angle 45 degrees with the normal it is making. Okay, observe the diagram. So here the light ray is incidenting on the interface with an angle 45 degrees. What is asking? The condition for total internal reflection. The condition for total internal reflection of this ray, the required refractive index of the prism will be prism or material. Okay. So instead of material, yeah, it's given prism. Okay. Right? What is asking? The ray is incidenting with this, then such that the refracted ray inside this totally reflected into the same medium. Then what could be the refractive index of this material is asking. Okay, what will be the refractive index of this material they're asking. Okay, right. I hope you understood this. Observe the diagram. Angle of incidence at the interface is 45 degrees. And inside that it is refracted into the same medium, and again at this point again totally internally reflected. Then what will be the refractive index of that medium they're asking, right? So look at this, observe the diagram here. Just let me explain the diagram first. The light ray is incidented, is making 45 degrees angle with the normal. So if this is 45, then here is R, and refracted ray is incidenting at a point B here. So see, at a point B, ray is refracted. So with the normal, this ray becomes, we'll discuss only this part here, only this part. Forget about this, only this part we will discuss. This just for a moment, imagine this as an angle of incident. Means this is incident ray at a B. This is incident ray. So I see. Why it is C? Critical angle. No, more than critical angle. So that's why it is internally reflected. Yes or no? Internally reflected. Right. Now look at this. Applying Snell's law of refraction at A, Snell's law at this point. Snell's law at this point. Okay. So sin I by sin R is equal to mu at this point. Sin I by sin R is equal to mu. Okay. Right. Snell's law. Then sin I is given 45 degrees. And sin R, we don't know. That is sin R here. Then sin R is equal to mu into sin 45. That is 1 by root 2. So we got sin R value. We got only sin R value. Now take out R from this. Take out R. Now take out R from this, that R is equal to sin inverse of, yes or no, sin inverse of 1 by root 2. So we got R value. So keep this as an equation of 1. Now applying the condition of total internal reflection at B. Okay, this part, from this part we got R value. Now we'll move to the B point. Now there incident angle. Observe this. IC, this part, IC is named it as an IC is equal to sin inverse of 1 by mu, because it is a critical angle. It is a critical angle. Then where IC is the critical angle, yeah, is given critical angle. Now R plus IC, what is R here? This one. Okay, R plus IC, okay, is equal to 90 degrees. Check it out. I plus R, both will be 90 degrees. Both will be 90 degrees. Yes or no? Right. So from this, 90 is nothing but 5 by 2. So sine inverse of, what is that? Sine inverse of, where is that? R value here. R value. Sine inverse of 1 by root 2 mu is equal to 5 by 2 minus, means this whole angle, R angle, minus is equal to 90 minus theta sine theta, 90 minus sine. Okay, so sine inverse of this thing is equal to, it's a 90 minus sine theta, so it will be cos theta. So cos inverse mu. So this can be rewritten in this format. Then here, look at this, root will be cancelled. Then this mu cancel. Then 1 by 2 is equal to mu square minus 1 is remain. And from that, if you simplify further, means take out mu square and simplify, then you get a 3 by 2 whole square, and mu is equal to under root 3 by 2. So what we have done here, what could be the refractive index of this medium they're asking. Okay, what will be the refractive index of this medium? So using this Snell's law and the relation between the critical angle and refractive index, so we obtain this solution. Okay, right. Now we'll see this problem. A light incident normally on a plane mirror. A light incident normally on the plane mirror. Here is the mirror. Attached to a galvanometer coil, retraces backwards as shown in the figure. A current in a coil produces a deflection of 3.5 degrees of the mirror. What is the displacement of the reflected spot of the light on the screen placed at 1.5 meters away? Observe this. Actually, it is the function of galvanometer. When the current passes through the galvanometer needle shows some deflection. So there some mirror arrangement will be there. So there we can see the image of the needle over there. Then we can take the readings over there. So that is another picture. But here the thing is, the light incident normally on the plane mirror attached to a galvanometer, okay, and retraces backward, shown in the figure. Okay, retraces backward this. Okay, see, observe this, going there and coming back. And current in the coil produces a deflection of, deflection is given, deflection is 3.5 degrees, deflection is given over here, right? So what is the displacement? Angle, they have given angle. Okay, they have given angle. See, this problem is related to what? Double the angle. When the mirror is deflected with the theta angle, then the angle between the incident ray and the refracted ray will be double. Keeping that concept in mind, see. So when a plane mirror rotates through a certain angle, the reflected ray turns through twice the angle of rotation. Yes. Yes or no? So here, yeah, observe this diagram here. Yes, is given in the problem 3.5 degrees, mirror is rotated, that is theta here. And once it is deflected 3.5, then incident ray, right? So incident ray at a point O reflects with the double angle, that is 3.5 and 3.5, that is 7 degrees. So angle of reflection and angle between incident and reflection given. So here, therefore, the angle between the incident ray AO and the reflected ray, okay, is theta is given 7 degrees. Now from the right angled triangle OAB, because as a mirror is reflected, then what happened? The ray is also reflects AOB, so it makes some triangle. Then what is asking actually, what is the displacement of the reflected spot? Initially it was at A, but now it is at B now. So what will be the distance deflection? D is asking, right? So from this triangle, so tan theta means we know only this value, okay, right? So tan theta is equal to opposite side by adjacent, that is perpendicular by base, that is BA by AO. The BA that we need to calculate, that is AB by AO, that is a D by 1.5. This length is given 1.5 meters. Now tan theta value, tan 7 degree value is here 0.1228, and from that you can take out D value and you can calculate this, and the value is 18.42. Yeah, what we have done using the same first principle that we discussed is to use it here, okay, and we'll move to the next problem. See, just looking at the diagram, observe the diagram. There is the water and air. In the water there is a fish, and in the air is a bird, right? And the water refractive index is given 4.5, and we know well refractive index of air is 1, right? And the bird is from the surface, the bird is at a height 36 meters, and the fish is at the depth 36 meters, and both are in same line of action. Yes, this is the situation. Now what they're asking, find the apparent height of the bird. Find the apparent height of the bird. Means apparent, in the very beginning we discussed the formula, right? Find the apparent depth of the fish. So for both of them the formula is this: depth of okay, yeah, the bird is an object and the fish is an observer. So fish is observing the bird first. Fish is observing the bird from the denser medium to the rarer medium. Hence the apparent height observed by the fish is, see, first condition has taken, because apparent height of the bird is asking. So with the help of this fish, you can see the height of apparent height of the bird. Yes, if you see from the bottom, we can see at what height the bird is appearing. That is nothing but apparent height of the bird. So formula is apparent height of the bird is equal to D by refractive relative index. Relative refractive index. Relative means what? With respect to both each other, that is air and water. Yeah, here D by, D is what? Original depth or original height, by ratio of refractive index of air to the refractive index of water. Refractive index of air is given 1, and refractive index of water is given by 4 by 4. So substitute the values here, you will get 36 by 3 will come here, 3 by 4, and you got 48 meters. But originally what is this? Originally 36 meters, but appears that as in 48 meters if you observe from right. So we'll conclude with this and we'll continue in the next class. Thank you very much.